Okay, in this video we're going to look at limits at infinity. What do I mean by that? Well, you recall from previous examples that when we look at a limit, usually this x approaches a very specific value. Okay, and that specific value might be 2. Okay, what is the limit as x approaches 2 of this thing? And we saw one of the easiest things to do was just to use direct substitution. So if x was approaching 2 here, I could plug 2 in and I would get 1 over 2 minus 1 is 1. Okay, but we're not approaching a specific number. We're saying go ahead and let x get as big as you want. Let x run as far to the right as you can. And what is happening to this function, if anything, as x does that? Well, the easiest way to see this is to look at a graph. Okay, so you can see I have my function here. And now let's look at the graph. Here it is. Here's the origin. And this is when x equals 1. This is when x equals 2. You can see that I have a value right around 1 here. And then x equals 3. It looks like we got smaller. And then as we continue to run to the right, we kind of run out of room here. Okay, so if I change my window setting and I look a little bit further to the right, let's go ahead and look at an x max of 20. Okay, now you can see a little bit clearer picture as to what's going on here. This curve, as x goes further and further to the right, it looks like this curve is getting smaller and smaller, and it almost looks like it's getting really close to the x-axis. Now, just based on this graph, we can't tell if it dips below the x-axis, if it comes back up. If this was all I had was this graph, you couldn't really conclude anything. Although, knowing what we know about rational functions, we know that this thing will never get below the x-axis. So just by looking at the graph, we can't conclusively prove anything, but it appears that as x goes to positive infinity, it looks like our y value is getting very close to 0. Okay, so from a analytical perspective, how would we do that? How could we figure out that this limit is equal to 0 just based on some mechanics? Well, you might be tempted to just plug infinity in here, and you need to be careful with that because remember that infinity is not a number. Okay, so what can we do? Well, one thing I like to do is I like to look for my variables. I like to look for the highest power of my variable, and in this case I have a power of 1. Okay, a power of 1. So what I'm going to do is I'm going to multiply the numerator and the denominator by the same exact thing. In other words, I'm going to multiply the numerator by 1 over x and the denominator by 1 over x. Now look what happens when I do that. Okay, I actually get a new function, and in my numerator I get 1 over x, and my denominator x times 1 over x is just 1, and negative 1 times 1 over x is just a negative 1 over x. Okay, another way to think about it, if this confused you, another way to think about it is just dividing every term by x in this example. And that's legal to do. I did it this way so that you can see that this thing right here really all we're doing is we're multiplying by 1. So we're not changing the expression at all. Okay, now what we can do is we can look at this new function and just imagine what happens is this x gets really big. Well, what happens if this was 10 million? Well, 1 divided by 10 million is a very tiny number. Okay, same with down here. 1 divided by 10 million is a very tiny number. Well, as this x gets really big, this number gets really small. This number is effectively 0 for very large values of x. It's not 0. I'm not saying that it is 0. I'm just saying effectively, as x gets really big, effectively, it's a very tiny number that's very close to 0. Same with this guy. Okay, this is also effectively 0. Well, what's left up top? Now, really, we have a 1 up here. We don't have 0, but we really have a 1. No, I'm sorry. We have a 0. Little brain malfunction there. So we have 0 up top. And down below, what do we have? Well, we have 1 minus 0 is 1, and 0 over 1 is 0. And there we go. Okay, well, let's look at the other example. Okay, let's try the same trick with this guy. I guess before we do that, let's go ahead and look at the calculator to see what the graph looks like, to give an idea of what we think the limit could be. Here we go. Okay, here we go. So as x runs out to positive infinity, it looks like my function is getting flatter and flatter and flatter, and it looks like it's hovering right around this number right here. Okay, I don't know what that number is. You could certainly go to your table, okay, and just plug values in that get really, really big. If I plug in a 1, I get 1 back. 2, I get 0.8. 3, I get 0.75. Well, let's try 10. And I get 0.689. Well, let's try 100. Okay, 0.66. Let's try 10,000. Okay, and it looks like the bigger we get, the smaller we're getting, but it looks like it's starting to plateau out a little bit. This kind of looks like 2/3 here. Okay, so how do we find that analytically? Well, we look to our function and notice the highest degree on our x. The highest degree on our x is a 2. There's really a 1 right here, but the highest degree is 2. So really what I want to do is I want to multiply my numerator and my denominator by 1 over x squared. And really, again, all I'm doing is I'm multiplying my entire function by 1. 1 over x squared divided by 1 over x squared is just 1. Well, what's my new function? My new function is 2x squared times 1 over x squared. My x squares reduce, and I'm left with 2. In my denominator, don't forget to distribute here. If I multiply those two together, I get a 3. And if I multiply these two together, I get an x over x squared. Now that's going to reduce. So I get 2 over 3 minus 1 over x. Okay, here we go. So now I can go ahead and I can effectively plug this in. I'm not really plugging it in. It's more of a virtual plugging in. You're just kind of thinking about what would happen to this overall expression as you let this x get really, really big. Well, what's going to happen to 2 as x gets really big? Well, it's just going to be a 2. Same with 3. It's just going to be a 3. And as this guy gets really, really big, 1 divided by a really, really big number is effectively 0. Okay, so I have 2 over 3 is 2/3. Okay, just another way to think about limits at infinity. What I would do first is I would probably graph it, maybe look at a table and let x get very, very big and decide what is my limit, if anything. And then I would come and I would do this little trick of dividing out by the highest degree of that, not dividing out by the highest degree, but dividing out by x raised to that highest degree. Okay, so that's how I deal with certain examples that involve limits approaching infinity. I hope that made sense to you. We'll see you around.